The New Quantum Era,
a podcast
by Sebastian Hassinger
and Kevin Roney.
Welcome back to the New Quantum Era. Sebastian here with you. I'm flying solo this week. Kevin's taking a well-deserved break. And during that break, we got a really unique opportunity, an invitation to the ribbon-cutting launch event of the installation of an IBM System 1 on the campus of Rensselaer Polytechnic Institute in Troy, New York. So I took that opportunity in Kevin's absence and went to RPI, spent a few days there meeting all of the people involved in the project, learning more about what was involved in actually making that happen, and what their plans are for using it, as well as attending a bunch of talks and by other researchers, by the NSF Rising Stars and others. So it was a really great event. I really enjoyed myself, and huge thank you to Rensselaer for inviting me and hosting me there. This episode will be a recording of a panel discussion that I hosted on Wednesday night of that week. So there'll be a discussion with faculty and staff from RPI who you'll meet and hear from as they discuss sort of the decision to purchase the IBM system, which, by the way, is the first commercial vendor deploying a quantum computer on a university campus in the world. So quite a historical event. And what was involved in that effort and then what they're thinking about doing with that device. So it's a really interesting discussion. And for subsequent episodes, for the next few episodes, I took the opportunity while I was there. They hosted me or provided me with the use of a podcast recording studio, which was a huge luxury. So in between talks and other events, I was able to grab time with a number of different IBMers involved in the effort, as well as visiting researchers who are providing talks on various topics. So we'll have a number of episodes from RPI over the next few weeks, and I hope you enjoy.
Welcoming our host this evening, Sebastian Hassinger.
All right. Hi, everybody. Welcome to the New Quantum Era. As John mentioned, I've been hosting a podcast with my co-host Kevin Roney for about a year and a half called the New Quantum Era, and I'm really thankful for the opportunity to join you tonight. This is an historic event. Rensselaer is going to be the first university that actually owns and operates a quantum computer on their own campus in the world, as far as I know. And that's quite a momentous occasion in many ways. And so with me tonight to discuss that, we're going to talk about, the context of that decision, some of the challenges, some of the opportunities that affords. Please join me in welcoming. Actually, what I'll do, I'll introduce you each one at a time, and you can do a little bit of a self-introduction. So, Jim Hendler, Professor and Director of Future of Computing Institute at RPI. So, Jim.
Hi, I'm Jim Hendler, Director.
Okay.
I'm a faculty member here at RPI, both in computer science and cognitive science in our web science program, and I've been running some of our research into looking at originally AI innovation, now overall computational innovation.
Thank you. Jackie Stampaglia, Director, Client Information Services, .cio.
Yep. Hi, I'm Jackie Stampaglia. I am the Director of Client Information Services in our central IT organization, and I've been at RPI for 27 years. A lot of that time I've spent in research computing, And most recently, I have been very involved in the installation and startup of the quantum computer here at RPI.
Thank you. And Osama Rasidin, research professor, RPI.
Research scientist, yeah. Yeah, hi, I'm Osama Reis. I am a former PhD student at RPI, and I stayed on as a research scientist because of the incoming quantum computer. And I'm interested in using quantum computer for engineering applications.
Excellent, thank you. And last but not least, Lucy Zhang. I can just barely see you all the way to the end, Lucy. Professor of Mechanical Aerospace and Nuclear Engineering here at the school.
Hi everyone, I'm Lucy Zhang. I'm a professor in Mechanical Aerospace and Nuclear Engineering Department. I am a engineer. We're users of all these potential new computers. My research is on computer algorithm, developing computer methods to solve engineering problems.
Awesome, thank you very much. So, Jim, I'll start with you, the Institute for the Future Computing. I assume you were involved in the early stage of the discussion to make this decision. What, in your mind, was sort of the leading rationale behind wanting to, have an on-premise quantum computer as opposed to accessing it remotely?
So those of you out on a podcast can't see me, but if you saw the gray beard and the gray hair, you'd realize I've been around for a few years. And from day one, a lot of my interest in computing started when I went to a school that allowed us to actually touch the computer and seeing and interacting and learning not just to be sort of a remote user of something, but really to get an understanding of it. The other thing is, one of the things that attracted me to RPI after I had been at another university for over a couple decades was very much RPI's philosophy of giving access to these things. So, for example, at my previous school, if I wanted to use our supercomputer, I had to get a fairly large grant and pay a lot of money for the support of the machine. Here, we actually, and I give great credit to John and Jackie and some of the other people, have created something where that financing is somehow built into the whole magic of the thing that I don't understand. But, my students are able to use it for free. I can use it with undergraduates, so we can do undergraduate research, graduate research. And so when the idea of the quantum computer came along, we really talked a lot about, what was the future of computing? And, sort of where did the innovation come from? The innovation comes from students. Both undergraduates and graduate students, and having the machine here, having the access, having the dedicated queues, et cetera, with that same, at least, philosophy of we want you to use it. It's not here as some kind of beautiful thing to go look at and watch other people use. It's get hands-on, figure it out, and make it do stuff. And, I think that was really, to me, the compelling argument.
Jackie, you were involved from the beginning as well. Was that sort of the thinking, was turning it into sort of an unmetered resource or relatively unmetered resources?
Yeah, I think that one of the things is, and to follow on what Jim said too with our supercomputer, is just having those resources here. Seeing is really believing too. And I think so much of what we do in computing today is in the cloud, and we're so far removed from it that it's really nice to have these systems here, and having access to them for our whole community is really a great thing.
Yeah, and I imagine, as you said, you've got quite an impressive supercomputing installation here as well. It goes back a long time. You've been in the HPC kind of space for quite a while. Yes. Are there elements of sort of physical deployment, physical solution architectures that you think may be able to be explored because these devices are both sort of on-premise?
Oh, yeah, definitely. A lot of structurally, environmentally, the cooling, the power, all those things. We have learned so much our first system was installed in 2007 down at our supercomputer center. Having that knowledge, I think, really helped us even with this installation now, and working very closely with the IBM team, which we did back in 2007 and again in 2013 and 2021, I believe, 2020, yeah. So.
Yeah, before I go to the other panelists, I have to ask you, what was it like to or help install a quantum computer in a chapel from the 1930s here?
So that was pretty challenging, but it looks great.
Yeah, it does.
It's really beautiful. So there were many challenges. I could point out a lot of them, but one of them was the quantum computer is installed in a vitrine with 10 by 10 glass, and finding a way to get that in. And some people, I think, have probably already heard this story, but we had to bring it in through some windows because we didn't have a door that could handle bringing that in. So.
You mean the chapel wasn't designed for easy access to a quantum computer? I don't understand. Seems like terrible oversight.
Right, and I mean, since 1980, it's had a data center in it, and even just having a traditional data center wasn't enough for the quantum computer, right?
Yeah, they are exotic animals for sure. And Osama, you were involved fairly early on in the early deployment of the computer as well, right?
Yeah, I did test out the quantum computer a bit, but for
unofficially, I heard. Unofficially, though, yeah.
Yeah, but as far as the installation and stuff is concerned, not directly. I was doing my PhD at that time.
Right. Okay, and so I mean, we talked a little bit about sort of the possibilities of exploration of having this device on site. I guess Osama, from your perspective, you're coming at this from more the algorithms and the software programming a quantum computer. Mm-hmm. Are there ways in which you see that being explored in the CS department that are enabled in some specific way by having it on premise?
Yeah, definitely. I think not just on premise, even having access to the quantum computer. Normally, when people are studying quantum algorithms, they run on simulators. But when you actually start running on an actual device, it's like skipping a step going up or down the stairs, because you're just hit with all these errors. And once you actually start running on the device, you need to keep all of those things in mind. And having access to those aspects, experiencing them firsthand, is very important in actually building real world applications.
Right. Yeah, and that sort of brings me to Lucy. I mean. In your department, Lucy, I mean, you already deal with, as you said, writing software for simulation. Mm-hmm. Are there specific areas that you're interested in seeing how quantum computers may be able to help?
Yeah, I mean, there are quite a lot. I mean, you look at all these engineering industries today, looking at automotive industry, aerospace industry, or material science discovery in general, like all of these potential applications, they all need modeling. So it's very, very heavy, and if you go into these industries, you will see that they don't just build something out of scratch, out of thin air. They have to do predictive models first, and then test it, iterate it, and then potentially have everything, all pieces worked out before they actually build the actual thing. So it's a very heavy component in the engineering industry. So having powerful computers are very, very important. That's what we've been doing all day long, is trying to use the fastest computers out there to come up with algorithm so that we can do all these predictive models. I mean, nowadays you look at people looking at digital twins of systems, and that's not possible without good computers. I mean, right now people call little pieces as digital twins, but the concept is there, but in reality, it's so difficult to implement without a good hardware and software in the background.
Interesting, yeah. And Jim, like, you've been involved, as you said, in technology development for a very long time. I think you mentioned DARPA to me, in fact, and I just wonder what you think about the role of collaboration between academia and industry and the public sector sources of funding to drive this sort of stage of technology development.
Right. So there's a somewhat pervasive myth that industry does applications, universities do curiosity-driven science, and sort of throw that over the wall to industry to figure it out. But when you actually look at the history of a lot of things, I don't care whether you're talking airplanes or you're talking the Brooklyn Bridge or you're talking the quantum computer, you're really looking at something that needs these partnerships. You really need somebody who's saying, look, I realize it won't yet solve this business problem, but if we someday want something that can, we have to start now in that direction. And that's traditionally been the universities. But now the question becomes, what directions for what problems, right? We're facing as a species these global challenges, climate change and fresh water, and we can go through lots of others. But if we can't learn how to do something with those and do it in a way that transitions to applicability. So we can have the greatest algorithm in the world for predicting something. If no one can turn that into something that actually becomes practice or practical, that's a problem. In an engineering school, you do have a lot of that knowledge about how to build things, but you still need the science and curiosity at the beginning. You need the interaction. So I think our relationship with IBM was actually, some years ago I wrote a joint article with someone for the Proceedings of the National Academy of Sciences magazine on university industry partnership, some of what you have to do to get it right, but most importantly, why it leads to good science. It leads to science that's meaningful. It leads to doing stuff that, you'll forgive me for quoting the RPI motto, but it's the thing that lets us change the world.
And Jackie, the way that the supercomputing facility has been utilized, does that sort of bring that kind of industry academia collaboration into play?
Oh yeah, definitely. I mean, the RPI researchers that we've had using it have brought in industrial relationships they've had. So working with industry partners, they've made use of the system as well.
Right,
yeah.
right. And that's, I mean, I assume that'll extend to the quantum device as well.
Yes, the plan is for that to happen.
I guess one of the huge challenges, I think, with quantum computing in general, and I'd love to get your view on this, Osama, part of the problem is that it's operating under a completely different computing paradigm that has a lot more to do with physics than classical computing does. And it's really difficult to get business leaders and technologists in industry to wrap their head around what that means in terms of the types of problems to approach. Do you have any sort of tips for how to make that happen, or a perspective on that?
I mean, a lot of work has been done in developing algorithms, but I think the first advantage that we might get, or the first use case, is definitely going to be using quantum computers to simulate quantum mechanics. And that doesn't mean that it's just some physics problem. This is something that is relevant in engineering, and I keep bringing up this example of multi-scale modeling. So that is something where you try to simulate the properties of materials, and then you start sending that information to larger scales to simulate maybe even like an airplane or something, right?
Right.
So I think those use cases might be coming very soon.
Right. Lucy, does that resonate with sort of the challenges that you have? I mean, often large-scale simulation is dealing with in approximations, and you're making guesses along the way as to what is the relevant data and what data you can afford to throw out. Is that sort of where you see potentially quantum computing being able to provide some more precision in areas that need it?
Yeah, absolutely. I mean, it's not just large quantities of parameter that we have to look at. It's also, there are uncertainties in these parameters as well. So that opens up, a whole new space that we haven't got a chance to explore yet. And right now we're just very, deterministic. A lot of them are very deterministic based on partial differential equation with some boundary, fixed boundary conditions, and we get a set of solutions. But it's in reality, the nature doesn't end just there. So yeah, totally, it needs a lot more.
And I guess also, I mean, I imagine in aerospace there's often problems that have at their core material science problems like corrosion and stresses, and at that level you are dealing with a quantum system at the material level. It's really interesting. Oh, go ahead.
So certainly materials and material, physics behaviors like corrosion, for example, for sure, and also, material discoveries. A lot of that needs random collections of, parameter spaces, and how do you put that together randomly without, having explored all of it? So, that is a very heavy space right now that we can get into. And like I mentioned, right now, you do a crash test, right? So you build a car, you design a new car, you have to do those crash tests. You don't just crash a real car first, you do all these simulations first. And there are a lot of, uncertainty, probability in those physics problems as well. So a lot of spaces.
Yeah, and Jim, you and I were talking earlier, seems like a good opportunity to bring in the unholy marriage of quantum and AI, which everyone wants to tie together. And there is some sort of relationship there, but it's very complex. But that multi-level kind of approach that ties together machine learning for a large problem space and then simulation is really potentially powerful, right?
Yeah, so we were talking about a model that I'm very excited by. So let me take one example. Right now, a company called DeepMind has created something called AlphaFold. You give it a protein description, and how a protein folds is a very important piece of the biomedical story. But it's not the whole story. The real story is how that folded protein binds to various things with various functions, which happens at a quantum level. So what happens is you take a protein description, you run it through AlphaFold, you get a few good examples. You can now go to the quantum machine and really model at the quantum level what's going on and say, okay, here's one that looks like it really works. Now, you're still in the probability space, so you've got some good probabilities from the AI, some really good probabilities from the quantum model. You now go over to your traditional modeling and simulation and say, okay, let me test this one, because the FDA is not letting me, put this drug in to any people until, just because I say, hey, the quantum computer said it might be a good idea. So you're looking at sort of something that takes a very large set of data and turns it down to a few probabilities. Something that takes those systems and puts them together at a very deep level, and then you can go to something that can really say, okay, now we go to the kind of thing Lucy's been talking about and say, let's really see, does this make sense? But the thing is, if you try to use any one of those technologies alone to do this problem, the AI won't give you that precision. The supercomputing can't run through 200 million proteins to find you the best folds. The quantum computer can do the quantum level analysis, but it really, isn't the right machine to do sort of the high level, when I hit a table, my hand doesn't go through it, right? But theoretically in quantum space it could. I mean, it's just the probabilities are so low they don't happen. But when you're talking about a protein binding to a target, that's exactly where it's happening, is at that quantum level. So we need to be able to put these things together in new and imaginative ways. And I think the marriage of these different sort of heterogeneous and composable systems is going to be absolutely crucial to the future of computing.
And Jackie, that sounds like a problem statement, a solution architecture that's tailor-made for what you have on campus now. You've got all those components. Have you started thinking about how those HPC classical compute resources will be integrated with the quantum computer?
Well, yeah, we did today, right, Osama? So one of the workshops we had today was quantum HPC integration.
I might have looked at the list of workshops.
Thanks for that.
A little bit of a cheat, yeah. We're starting to look at that. I think it's going to be very exciting working with IBM to do that, to get that set up. That's great. And Osama, coming back to sort of the algorithm perspective, so do you sort of, the algorithms you were interested in, are they primarily sort of in that Feynman way of thinking of quantum computers where it's if you want to simulate a quantum system, you need a quantum device to do it?
Right. So from a very practical perspective, yes, that would be like the first early applications. But I think from a computer science perspective, getting to know what the complexity of solving a problem is, I think that's very interesting. And that's actually where I started my research. During my PhD research, I was more interested in the complexity of solving linear systems. We can get some exponential speedups for some particular cases.
That's great. So then those are algorithmic primitives are more generally applicable then. Is that fair to say?
No, not generally applicable.
Well, applicable in multiple types of
types
higher
of
level
problems,
algorithms.
Given that you satisfy their conditions that, for example, the condition number of the linear system scales well or something like that.
Yeah. And I mean, there's it feels like listening to Lucy, there's kind of a high level sort of industrial application perspective. Listening to Jackie, there's sort of an operational perspective. When I look at the algorithm research that's going on, it still feels very low level. It feels like closer to assembly language than the high level languages we're used to in classical computing. How do you see sort of bridging that gap between where the computer science is with quantum computing right now to where it needs to get to for these sort of large-scale end-to-end solutions?
Yeah, I think it's a long way to go, I
Yeah.
feel like, and for sure there have been quite a lot of theoretical foundations that has been built, 10 years ago, even 15 years ago, about how to solve a linear system, like a linear algebra, right? So that's potentially what a lot of engineering physics are governing equations are. We have a lot of nonlinear equations to start with, but we try to linearize it. I think the easiest or the fastest way to think about this is that you have all these complex equations or large size equations, like Osama was mentioning about multi-physics interactions and all of that. You can still start by boiling down to linear equations. You linearize it first. And then I think we finally have hope because all those theoretical foundations that people have been developing for linear functions and linear equations, we can finally test it. We can test it. We have a way to explore it now. And once we have that all taken care of, and then we can start getting into more complex systems, like all the stuff that we want to do. And in fact, 30, 40 years ago, that's how all the mechanics people started this, right? So, you look at all these industries, they didn't have anything like computer algorithms before, and then they started with theoretical math, in the background first, and then when the computer scientists figure out the software, the language, and all that put together, we're like, okay, finally, we can finally test out our theoretical foundations that we've been building.
Right.
And so then eventually 30 years, passed, and then we said, okay, now it's finally mature and becoming products. And now it's becoming a standard for all of these design or applications. So I think we're getting there. So I think we're as potential users, we're always trying to adapt. We have foundations there, and we're keep on adapting.
Yeah. That collaboration around innovation sounds very much like what you were describing, Jim. I mean, what do you see at this stage, given you've seen technology cycles in your career, what do you think is most important to focus on at this stage?
Yes, so I actually think that we've touched on a lot of these things, but that computer level, that move up from assembly language to something, I think it's very important. One of the people who will be here tomorrow is one of our rising stars, Andrew Young from MIT, made a great point in a talk he gave here a few months ago, which is that there's a lot of ways to make errors in quantum computing that cause the thing to sort of collapse. And if you make one of those errors, the way he described it is you end up with a very slow, very expensive classical computer, right? Which is not what we're after, obviously. So really learning how to build some of these software things at a level that's quantum safe, but it's still at a conceptual level, the chemist doesn't want to learn physics. The material scientist doesn't want to learn, quantum gates. What made life change was first Fortran and then higher and higher level languages. So, my students are now doing things in neural nets that I couldn't have imagined 20 or 30 years ago by writing 4 lines of Python code, right? Which compiles down into tens of thousands of machine instructions, right? We're not there in quantum, and we're going to need to learn to get there, as well as how to have some of these things interact, so that if my AI system says, here's a good potential candidate for something, how do you represent that over to the quantum machine? Things like that. So again, we're going to need the scientists, the engineers, the people who are actually going to want to solve real world problems with these machines need a toolkit. And, one of the best ways I've seen over the years of getting those toolkits built is by solving real problems, saying, okay, how did we do it? What could we reuse? Et cetera, et cetera. And I expect over the next few years, we're going to see a lot of that same thing happening in the quantum space here, where our students are using existing things like, this is really great, but if we added this, or if we changed that, or if we could embed it in this, then it becomes much easier, and then the next person comes along and takes and builds on top of that. And I think it's, we've seen 50, 60 years of that continually happening in the traditional computing space, and now quantum is coming into the picture, and we need to figure out, sort of how we bring that into the family, as opposed to becoming a dysfunctional family going off in different directions.
In hopefully less than 50 or 60 years.
And hopefully less. Well, let's just say it's been a very accelerating curve.
Yes.
And, we always look at the graphs now on exponential charts, so it looks like a straight line, because otherwise it just shoots up so far you can't even see it.
So, Osama, your PhD was focused on more complexity and the theoretical side of things. Do you see, now that you have access to a real quantum computer, are you seeing a path towards making, tackling more real world problems with that kind of background?
Yeah, so the problems that I was working on, hopefully once we have error-corrected computers, on those we could potentially run those kinds of algorithms. But I think we have a long way to go in terms of that. There's a clear roadmap though. And I think it's going to happen in the next decade or so, if not earlier.
Yeah. Certainly. I mean, IBM's paper saying that they can do 12 logical qubits out of 288 physical qubits. That was pretty astounding. So, I mean, there are definitely logical qubits, error-corrected quantum computers are on the way. What's the main sort of task now before we have those error-corrected qubits? Is it still theoretical and sort of trying these things out on physical qubits, or?
I think right now the main task to prepare for error-corrected hardware would be to start building up the software stack and make things more modular. So, for example, there's this famous algorithm called the VQE, Variational Quantum Eigensolver. But at its core, it's just an eigenvalue solver, right? And this is a particular problem which is solved not just in physics, but in engineering and in a lot of different fields. So I think there is also this aspect of being able to learn the language and cross bridges, because people hear quantum and they kind of get spooked from it. Right. So I think that bridge also needs to be crossed for applications to come in.
So do you see sort of co-design opportunity with Lucy and other professors and other schools of engineering and sciences?
Yeah, definitely. A lot of these fundamental problems like QAOA, VQE, it's like an eigenvalue problem, combinatorial problem, linear system problem. They show up in all of these different areas of study, and there's definitely a potential for that.
And Lucy, is there anything, I mean, do you think you're going to need to, Maine will have to introduce more QIS sort of curriculum in order to sort of meet the theorists halfway at this stage?
Yeah, absolutely. I just sent a student to Osama.
We also are getting a new course, right, the next semester?
Perhaps, I don't know about, yeah, likely. I'm currently at the National Science Foundation as the program director. So I see a lot of workforce development type of calls now that, people want to build it up because potentially that's a workforce that would be missing if we don't act now. So certainly there are so many opportunities, and for the, even for the current undergraduate level, I tell my son the other day, I said, did you know that we're going to have a quantum computers? He was so excited, right? So I think that next generation, they are our hopes, right? So they're interested, and then I think by the time they grow up, or even our current graduate students, they have to be somewhat informed. Kind of go along with the, whatever, just be informed in some way. So because the workforce market will be missing those talents. So for sure, curriculum, development, and definitely, some type of training, either whatever it is, could be on the side, could be, just purely out of interests. We can build that up, and then we have a computer in hand that we could do that.
Yeah, and workforce development is the National Quantum Initiative mentions it quite a bit in that bill or that law, and obviously the NSF has enormous amount of resources dedicated to that. I wonder, and this is an open question for anybody, what do you think RPI will be able to accomplish in terms of curriculum development with the unique resource of having an actual device on campus, which is uniquely a unique situation to be in?
So let me jump in and, well, I absolutely think there'll be a lot of things happening in our curriculum. Frankly, I think the most exciting thing will be what's happening outside of our curriculum, in project spaces, in a lot of our classes. The last thing you do in the term is a group of students works together on a project. And if you've listened to the sort of applications we're talking about in some of these different levels, I think for the foreseeable future, if you're going to use these technologies, you're going to need someone who really understands the problem, someone who really understands the quantum computing aspects, some other people who may know some of the software techniques or the mathematical equations, right? And sort of in the early days of computing, it was very much like that. You would sit and you'd write the program by yourself, but then you'd have to go find someone who actually understood what it was supposed to do to check that it was actually doing it. And I think we need a lot more of that kind of interaction on a much deeper level. So I think a lot of our curriculum is going to include both learning the depth of this is the math, this is the physics, this is the programming style, but also those crosscuts. Let's look at this problem, right? And if you've looked at the posters, there were some really nice ones, say, from some students who, in a project course, got some data from NASA, decided to try analyzing it using various learning techniques, including the quantum learning techniques, which they ran on the simulator, and sort of by next week, they'll be running it on the real computer and be able to get us actual, these are the comparisons between this kind of network, this kind of simulator, this kind of actual machine, and then we can watch those things change over time. And it took a bunch of students, some who understood the problem, some who understood the computing. And so I think we're going to see, both in courses, but especially outside of courses, this kind of teaming and doing it. And here I mean undergrads, grads, faculty. I mean, these cross campus teams are just really going to have to, we're going to have to find a way to enable that, make that work. We have a lot of those mechanisms already in place at our PI. It's one of the things that makes us special. And I think the quantum machine is going to fit very neatly into that paradigm of students proposing things, people being able to advise on that, those things becoming the curriculum. So I actually see almost the curriculum as a what's the word, beneficial spiral. There's a term for it that I'm blanking on, but where each time round it gets a little better. Right? So I think that's what we're going to see happening here is the courses will enable the students to do things that will enable new courses to be designed, that will enable the next set of students to do even better things, and I think that'll go very quickly.
That's interesting. And I guess this is for everyone again. To what degrees? Because every time you look at the challenges, the progress, we've been talking mostly about applications and sort of finding these commercial or productive uses for quantum computers in industry. There's also the whole topic of how to make quantum computers work better, right? Error mitigation, error correction, you mentioned, Osama, the algorithmic primitives themselves. What's the balance at RPI in terms of focus? Is it 50-50 in terms of trying to improve the field versus trying to find applications to the field? Or how do you see that split? Sure, anybody.
Yeah, I think both sides need to be tackled at the same time. And I think recently, we've been surprised by the amount of progress that is being made. I think just this past week, IBM came up with a new code for error correction, which requires orders of magnitude fewer qubits. So I think putting efforts into both ends, into making the hardware better and also trying to improve the applications and the software stack, I think that would make it even better. We are going to get to the end goal faster.
And Jackie, is there, in the supercomputing center, is there sort of a tradition of sort of feeding, that kind of fundamental improvement back into the vendors, into the technology?
Yeah, definitely. There is. We have a partnership with AI, which Jim, the AI Hardware Center, which Jim maybe could speak to a little bit.
So for a long time we've had an AI relationship. Well, we've had relationships with IBM for a long time. For the past few years, we've had a very heavy one in AI that's now expanding to AI hardware, microelectronics, and quantum. And the idea of these 4 tracks is not to be 4 parallel things that don't talk to each other, but to really encourage this kind of interaction. Jackie's role in this is making it possible for us to do it. My role is convincing the students that they should be doing it. But more seriously, it really is the case that there's going to be a lot of exploration going on, and I think this is a great place for it. And what we've done as our supercomputer has evolved from very much an equation-based system to something where we ran some of the early AI techniques to where thanks to NVIDIA and some of our partners, and we'll hear from some people tomorrow who've been very involved in this. Hi, Curtis. Now our supercomputer is essentially an AI-enhanced supercomputer, so it can be used for standard linear supercomputing and some of these other modeling and simulation techniques, but also has tons of GPUs, which we can use now for these AI learning techniques. And so we've been able to, rather than having to go off into a cloud, rather than having to depend on other people's software, are able to do our own experimentation. And then working with IBM, who understands some of the internals and have been able to improve some of that. Some of the other things we've done together. So in the past 5 years, we've had well over 100 joint publications in top conferences and journals with RPI and IBM authors together. And I think in quantum, we're already having the discussions about how we're going to make that keep happening, how we're going to grow that, how we're going to really create this partnership as a partnership.
One of the other things we talked about today, too, was classical computing and how to integrate then quantum computing into different parts to further along what the research is. And that was an interesting conversation, I thought.
Yeah, I think even to do quantum computing, you have to come up with the circuits, you have to make them efficient, you have to convert your circuit into the laser pulses or microwave pulses, etc. Then for that also, to make it efficient, you might need to heavy classical computing resources.
Right.
So that's an interesting integration.
Yeah, that's the other quantum AI meaning that I referred to earlier. Yeah, I mean that feels like in order to, when we have some amount of quantum advantage from a quantum computer, we're going to need to have very tight integration with the classical computing resources in order to not lose whatever advantage we have in the overhead of sort of the pre and post processing. Is that sort of where you're
Yes, yeah.
going with
That's-
that? So
that's
is
what
that
we're
just
talking about today.
faster network interconnects, or is it like actual physical co-location in a rack, or I mean, how are you thinking about that?
Yeah, I think faster network interconnects, definitely. Also, for if you have like parameterized quantum circuits, then running those circuits on the fly, one after the other.
So that's more
quick suggestion.
classical computing power close to the QPU, so that you can flip around parameters in the circuit without having to round trip it all the way back.
Yep.
Yeah, got it. Interesting. And so, like, if you're trying to make this available for that kind of very open-ended experimentation and exploration, Jackie, like, how do you manage a resource like that? You've got one quantum computer. There's probably going to be more than one person wanting to use it.
Yes.
Is it back to timeshare days? Is that what we're doing? Or?
Yeah, well, we did talk about our Slurm scheduling, so we use the Slurm
Okay,
scheduler
yeah,
if you're
yeah.
familiar with that. It reminds me of something many years ago when we were working with IBM. One of the folks at IBM, he was an IBM fellow, who I would work with periodically to get people, because IBM was using our supercomputer too. And he said to me, you know, the best you can do is always keep everybody a little unhappy. You don't want anybody too happy, because then everybody else will be very annoyed. So I think that might be our goal.
Distributed annoyance.
Distributed at a very low level.
Yeah. It really is a unique, I have not seen this level of sort of open-ended exploration with a device by an academic institution. And that's really exciting. I mean, it feels like, we don't know what we don't know about quantum computing. And it's this kind of, you actually said this to me in one of the earlier conversations we had, Jim. You said, if we don't explore in this way, it won't happen, right? There's sort of this open-ended exploration that's required in order to have that moment of serendipity where the insight happens, right?
You know, I take out my telephone and open ChatGPT and, play with it, right?
That's what you meant by having a relationship with AI? Is that
30 years ago or more, actually, oh God, more. We were doing, it was a PhD thesis to do the story. Jack went into the restaurant, he ordered a lobster, he ate and left, and get the student to answer the question, get the computer to answer the question, what did John eat? Right? I actually was the programming assistant to one of our PhDs who was working on virtually that exact problem. Today, while we were chatting, I actually asked ChatGPT that, and ChatGPT said, "Hey, lobster." So we've evolved this thing, and it seems like it magically happened overnight, but in fact, if you really trace this stuff back, you see different innovations, you see different kind of things, and I think I've been at RPI now 17 years, but I've been really working in this particular research space of trying to put these things together for the past 8 or 10, just the acceleration of which we've been getting, and the possibility, again, the joint work with IBM and other partners has really made this stuff accelerate. And a lot of that is because we can really try things. And that trial and error are crucial, because if we're going to ever figure out how to really use these machines right, we're going to have to make mistakes. And we have to be somewhere where that can be tolerated. And again, having the machine on campus, I don't mean we're going to make mistakes that cause it to blow up. I mean, we're make mistakes that cause the quantum equation to collapse, and suddenly, we're going to look at the computation and say, oops, maybe we better change that code or rethink how we're doing that. And I think that's where the real learning is going to happen, and that's really exciting.
And Lucy, like, if you imagine that kind of enormous progress over the next, say, 10, 20 years, and to the point where we have, at scale, we have sort of a quantum mechanics lab in a computer that's totally programmable. You can just program any quantum system and watch the evolution, see its attributes. What's sort of like the dream scenario from an engineering perspective for you? What would you be able to do if you could do that?
I think, I mentioned digital twins earlier.
Yeah.
I feel like that's the ultimate system level, capability simulation that we, as an engineer, I would like the computer to replicate in real time what the solution should look like for a whole system, not just parts of it, and not waiting for 2 weeks or 2 months for some results. I think for us that would be a dream. And certainly, a lot of things need to be in place beforehand.
Well, I'm just reflecting on that level of advancement that Jim's talking about. So, Osama, same question to you. If you imagine that sort of giant evolutionary leap over 10, 20 years, what do you think will be possible with that kind of quantum physics in a box?
Yeah, it's interesting when you say quantum physics in a box. I have a background in fluid mechanics, and I kind of look at quantum computers as like a wind tunnel experiment, but for quantum physics. I think something very interesting would be to simulate large-scale materials. Like the way, so there are these some phenomena that we cannot recreate in our simulations. For example, if you have a titanium bar, right, and if you run an electric current through it, it suddenly becomes soft, and you can machine it much easier. So if you can explore that kind of physics, like the excited state physics, I think that would be very interesting. And you could come up with new manufacturing processes, like you excite your material in the right way, you shine the right wavelength onto the material, and suddenly it's much easier to machine. So that would be like a dream scenario.
Right, almost like programmable materials in a sense. It sort of makes me think of, moonshots, it's a metaphor we use a lot for sort of these grand kind of scientific and technological missions, and it's a reference to the space program, which, there is no direct sort of benefit from landing on the moon commercially, but we learned so much in investing all that time and brain power that there were tons and tons and tons of sort of secondary and tertiary economic benefits and commercial benefits. Is that kind of how you imagine, like, again, this sort of material foundry in a box, simulation in a box? You could imagine like so many different like offshoots from that would be valuable.
Yeah, definitely. I think the same kind of discoveries could be applicable in other domains like fluids, perhaps. It's possible.
Excellent.
Some years ago, one of our honorary speakers was Craig Monday of Microsoft at the time. And at a dinner with him, Craig said, we really don't have an energy problem in our country. We could deploy enough solar to power everything. The problem is the lossage we get as things run through the wires and the cables and that. And he said, if we could solve sort of room temperature supercomputing, as it were, or at least reasonable temperature supercomputing, you suddenly have...
Superconducting. Yeah.
I'm sorry, superconducting.
Yeah, I do that all the time.
I sit next to Jackie. I'm automatically going to say superconducting. But really, in a sense, these things can really be world-changing technologies.
Yeah.
And, when you talk about running the electricity through a titanium bar, we know something's happening in there. Once we can start figuring out what's happening in there, that opens up the possibility of really looking at these lower-level technologies as well as these high-level problems, and then saying, hey, this gives us the tool we need to go after this next step and next step. So again, you keep saying 10 or 20 years. Frankly, I'm hoping it's 5 to 10, maybe less, because I think this stuff is going to move very quickly.
I agree. I mean, you can see the beginnings of these advances in the applications now. It's just, the time horizon extrapolation can help sort of crystallize some of these things. It's hard to see them when they're right in front of us sometimes. So Jackie, do you foresee, if there are that many sort of applications and uses for this thing, do you get a second quantum computer? Is there?
That's the question for me?
Where's your checkbook?
We'll take another one. Yeah, I mean,
I guess my question is, does that quantum data center, does that expand over time? Is that sort of...
Yeah, I mean, I'd like to say that we have, in the time that I have been here, certainly, and goes way back farther than that, our computational resources and capabilities, RPI, with generous gifts and other things have always carried on, right? So I don't think we're done by any means. I don't want to think we're done by any means. So.
Any last thoughts from anybody on the panel? This has been really interesting, but I want to make sure if there's any. Osama, it looks like you've got one.
Yeah.
Excellent.
Yeah, so quick story. So during my undergrad, I got my new laptop for my college degree, right? So during my undergrad, I had a laptop with a GPU, and back then, not every laptop had a GPU. And because I did have the GPU on my laptop, then I wanted to run my codes on the GPU, and I tried to do that with MATLAB, so I didn't get very far. But the same thing is with the quantum computer. Now that we have it on campus, it's available to us. Now there's the itch to actually use it and run things on it. So I think having access and being close to the computer itself, I think it does drive people to use it a lot more.
Mm-hmm.
Yeah, I think there's an undeniable, even psychological effect of just that machine sitting there in that chapel, in that beautiful setting. It makes it top of mind. It makes the imagination sort of start to run wild. So, well, thank you very much, everyone on the panel. Thank you very much, everybody, for being here. And that's a wrap.
Thank you.
Okay, that's it for this episode of The New Quantum Era, a podcast by Sebastian Hassinger and Kevin Roney. Our cool theme music was composed and played by Omar Costa Hamido. Production work is done by our wonderful team over at Podfi. If you are at all like us and enjoy this rich, deep, and interesting topic, please subscribe to our podcast on whichever platform you may stream from. And even consider, if you like what you've heard today, reviewing us on iTunes and or mentioning us on your preferred social media platforms. We're just trying to get the word out on this fascinating topic and would really appreciate your help spreading the word and building community. Thank you so much for your time.